Welcome back. In this recording, we're going to talk about work and energy. And these are two terms that are always linked in physics. And it seems like it's hard to come up with a real clear definition. And I kind of looked around and checked some sources, and I found what I thought was a pretty good definition of work. And I'm going to, write that here for you. And it's that work is equal to the amount of energy that has been gained or lost by the object. Now, work is a pretty common term that we have used probably a lot without even understanding a physics understanding of it, which means if I go to work, I'm doing something to earn money. Or if I get homework, there's something I have to go home and do to finish up for my preparations for the next day of school. Or maybe your parents have work for you to do when you get home from school that you're expected to work on. But in physics, it's related to energy. And you can see work is the amount of energy that something has been given or had taken away. If I put the brakes on in my car, you can probably imagine that that is a case where we're losing energy, where we're going from having some speed to not having speed. And that would be an example of negative work. And that's usually not too bad. Here's my issue a lot of times when we're doing these same types of things, and it's that energy, sorry about that, let me try to get this back in the right spot here. Energy is defined as the ability to do work. And that's probably the most common definition that I always kind of see. So this seems kind of confusing because each word is kind of used to define the other. And I guess one of the things you can kind of do is think about things have a certain amount of energy. So maybe this circle represents the energy that something has. And when I do work on something, I'm putting energy into this. That would be positive work. Or I'm taking energy out of this. That would equal negative work. If I do negative work, this would become a smaller circle. I have less energy than what I did before. If I did positive work, this becomes a larger circle, or at least that should be larger than what's up there. It's kind of a bad drawing, but if I did positive work on something, then this becomes bigger than what I had previously. So work is kind of a way to transfer energy into or out of a system. And energy is that thing's ability to do work or to cause some type of change in its surroundings and its environment. So it can be positive work, it can be negative work. Energy can be positive, it can be negative. It kind of depends on the type of energy. Now, if I kind of ask the class, what are the two types of energy, I'm guessing many of us could come up with these two terms, kinetic energy and potential energy. And then if I asked you, okay, well, what is kinetic energy? Let's try a different color here. Kinetic energy is a bullet, the energy due to motion. That makes sense. If something's moving, it has some types of energy. It kind of goes back to our car example. Potential energy, that one can be a little bit more confusing. This is usually looked at as stored energy. And there are many, many examples of stored energy. There is what we would call gravitational potential energy. There is what we would call elastic potential energy, like springs or rubber bands. Electrostatic. If you have a little chemistry background, you understand there are things like positives and negative charges, and they attract, opposite charges attract each other, like charges repel each other. There's probably a big kind of a general idea of just chemical potential energy. Try to undo that. And that's the idea of, like, I'm running a computer right now on battery power. There's some type of reaction occurring that's giving this computer energy that helps it run. As well as other things like nuclear potential, solar potential, and all these other types of things. That really kind of comes down to different types of internal energies that are being used to do stuff. So, for our purposes, we want to kind of break this down and make this a little easier. We're going to kind of focus right now on just the gravitational potential energy. Elastic potential and electrostatic will come up later on in later lessons. But to kind of clear this up, if I have kinetic energy, it depends on two main factors. EK, or KE, a lot of times it'll be, is equal to 1/2 times the mass of the object times the velocity squared. That squared is a huge factor now. That makes this much more influential over the total kinetic energy than the mass is. Another way of doing this very simply is this EK is equal to 1/2 mv squared. Potential energy, usually an ID is written as P. In this case, I'm going to put a little G after this because gravitational potential is equal to mass times gravity times the height. Simply, EP is equal to M times G times H. Now, there is no square term in here, so basically they have the same amount of influence over anything. Double the height, double the potential energy. Double your mass, double your potential energy. Gravity is relatively constant here. Gravity is usually equal to, again, this 9.8 meters per second squared. So that's not really much of a factor in terms of making it increase or decrease. But it does show if you went to a different planet, like Jupiter, which has 13 times the gravitational pull that Earth does, this would become a greater value. So when we go back to here, if you double your, just to give you some visuals, if I would, let's say, double my velocity, so 2 times v equals 4 times my energy. If I triple my velocity, 3 times my velocity, I'm going to have 9 times the energy. And you can probably guess if I go 4 times my velocity, that's going to be 16 times the energy that I started with. So, and 5, 25, and you can kind of see that squared relationship. So you can see how that gets much bigger. If I just double the mass, I have twice as much kinetic energy. Double or triple it, I have 3 times as much kinetic energy. So you can see how this velocity factor makes this get very, very big, very, very quickly. I'm going to just insert an extra slide in here because we need to talk about energy again. So I'm going to insert blank page. I'm going to make this the same as the other one, so I'm just going to set this with a black background. And kind of going back to energy now. The energy formula, we got to relate energy back to work. Our work formula, work is equal to force times distance times the cosine of the angle, theta. Another way of thinking about this is work is using force to add or remove energy. So force, distance, cosine theta, this is written a little more simply as work equals F d cosine theta. So this cosine function means only part of this force and only the part that goes in the direction of the distance is actually doing work. So, if I'm pushing downward on something like this, and let's just say this is the angle theta, let's say I'm just pushing on a box, and we're making this box move in this direction with some velocity, and I move at some distance that's equal to d. So the idea is cosine function, you can kind of break this up into horizontal and vertical parts. this would give you the sine function. This would be sine. This side here is your cosine function, which what that basically is showing you is only the part that points in the same direction as the distance is moving. That's the only part of the force that's actually doing work on this. And if you think about that from an energy standpoint, that's the only part that's making its kinetic energy really increase, because it's pushing it in the same direction that the velocity is going to be increasing or decreasing. So that's why we have this cosine function. It makes it very easy. You don't have to break this into its components. We can just let the cosine function kind of take care of that for us. So, to give you some like a visual example of, let's just say, and this is going to be brutal, but somebody's hand and they're pushing on a toy, let's just say like a toy truck, and they're giving that truck a push this way. So, my force is pushing it this way. It's making it move some distance in that way. Its kinetic energy will increase. So KE goes up. And that's a pretty simple way of thinking about that. Force giving this thing kinetic energy. If I lift a weight, if I have like a dumbbell or something like this where I'm now lifting this up, my force, again, is pushing this up, pulling that up, whatever you want to think about it as, and that's the distance that it's moving. So now I'm raising this up. I'm increasing this a certain height. So in this case, my potential energy, once it gets to the top, is now increasing. As I lower this weight, it's just the opposite. Now I'm lowering this down. I'm reducing the height. My force, I still have to push up on this to move it, but the distance that moves is downward. If I have something going this way compared to something going that way, that angle is 180 degrees. So if I go back to this idea of the cosine function and just look at that, the cosine, 180 degrees, is equal to -1. So what it tells me now is when I lower this down, I am decreasing my potential energy. And that kind of makes sense because I'm putting it at a lower height. So that's kind of part one of how energy and work are related.